Now, in the previous lecture or previous video, we had looked at second order equations, difference equations, where we had two distinct roots, and the case where we had multiple roots, where the roots were the same, the roots to the auxiliary equation were identical. Now we're going to look at the case of complex roots, and that involves imaginary numbers and oscillations, as we will see. So let's consider the quadratic equation a0x squared plus a1x plus a2 equals 0. And the solution to it we know is this quadratic formula. And in this case, if this component here, a1 squared minus 4a0a2, is less than 0, then we need to define this imaginary number I as the root of minus 1. So for example, if we take the equation x squared minus 2x plus 5 equals 0, we find that x is equal to 1 plus or minus 2 to the root minus 1 is equal to 1 plus or minus 2 times I. And we get that the first root is 1 plus 2i, the second root is 1 minus 2i, and we refer to that as complex conjugate numbers. So in general, x1 is alpha plus beta I, and x2 is alpha minus beta I. Alpha is the real part, and beta times I is the imaginary part. This occurs whenever, as I noted, this component or this calculation under the square root sign is less than 0. The general solution to the difference equation is now given by, and you'll see that it's identical. Before we had x1 here and x2 here. Now we've got k1 times alpha plus beta I all to the power t plus k2 alpha minus beta I all to the power t. The problem is that the time path derived using this mechanism for solution is not always clear due to that imaginary part of the solution. So we need to review a minute about polar and Cartesian coordinates. So if we plot on the horizontal axes the real numbers and on the vertical axes the imaginary numbers, and then take a vector r that goes out to alpha, the real part, and beta, the imaginary part, and we measure this distance as r. So this also would be measured as r along here. And what we do is we find this theta as the angle from the horizontal axis to the imaginary number along which this r is projected. So r squared is given by alpha squared plus beta squared. And r then, of course, is the square root of alpha squared plus beta squared. Now we also know that the sine of theta is given by beta divided by r, so that beta is equal to r sine theta. Now a summary of this is found on the last page of this particular video, and we'll come to that shortly. The cosine theta, so beta over r is the near or the adjacent over, not the adjacent, the opposite, because this is your beta height, over the hypotenuse. And for cosine theta, we find that it's the adjacent over the hypotenuse, as noted in that final page. So we find that beta is equal to r sine theta and alpha is r cos theta. So this implies that alpha plus or minus beta I is equal to r multiplied by cos theta plus or minus I sine theta. So recall that the circumference of a circle is given by 2 pi r. For r equals 1, the circumference is equal to 2 pi. So here we have r equals 1, and this distance here is also r equals 1 because we have a circle that goes in here. And The angle associated with an entire circumference is 360 degrees, which is equal to 2 pi radians. All right, these are radians, and we mark that as rad. So this really refers to rad equals radian. So I'll just call it rad from now on. So we have that 2 pi rads is 360 degrees. So pi rads is equal to 180 degrees. And 1 rad is simply 360 degrees divided by 2 pi, which gives us 57.3 degrees. Now, how many radians are there in this particular one? Well, we'll show you that it's going to be 0.75 rad. So we can write the general solution now as yt equals k1, and then in brackets r to the power t cosine theta plus I sine theta to the power t. And that comes from up here. Okay, so this is what we're looking at now and plugging it into our previous equation for yt, for the solution to yt. And we add to that kt, all in brackets now, rt multiplying cos theta minus I sine theta to the power t. Then there is a theorem by De Moivre which states that cosine theta plus or minus I sine theta to the power n is equal to cos n theta plus I minus plus or minus sine n theta. So then what we can do is we can take that t and bring it down. So then the general solution becomes RT, all in square brackets, K1 times cos theta t plus I sine theta t plus K2 times cos theta t minus I sine theta t. So now we let A1 equals K1 plus K2 and A2 equals K1 minus K2 multiplied by this imaginary term I. So then we have that YT is RT all multiplied by A1 cos theta t plus A2 sine theta t, where theta is now measured in radians or rads. The solution to the second order linear difference equation is clearly a cyclical path for y over time because sine and cosine functions are periodic, so we get oscillations. And we can see that here. So this black line is the sine function, the sine of an angle phi, where phi is measured in radians. So this would be the full circle here. So this would be 2 pi, this would be 1 pi, and this would be half a pi and 3 halves of a pi. All right, and notice that cosine theta begins at 1 and hits 0 at the first pi over 2 and follows this in opposite to sine of phi. And you should know that from your high school trigonometry. In the case of complex roots to the auxiliary equation, we need to find the angle whose tangent is given by minus A2 over A1, where A1, you'll recall, is K1 plus K2, and A2 is K1 minus K2 all multiplied by I. Note, does minus A2 over A1 contain imaginary numbers? It turns out no, and we're not going to prove that here, but we will show it in the final example that we used. So we need to find a delta, measured in rads, for which the tangent of delta, so delta is an angle, is equal to minus A2 over A1, which is, by the formula for a tangent, is given by sine of delta over the cosine of delta. Since different numerators and denominators can give the same ratio, an additional parameter is needed. So we're going to introduce A3 as a scale factor, so that A1 is equal to A3 cos delta, and minus A1 is equal to A3 sine delta. So we substitute for A1 and A2 in this formula here, in this component of the function that we were looking at up here. Okay, so we're looking at changing this yt function as follows. So we substitute for a1 and a2 in this expression of that above function, of a solution rather, to yt, and that gives us a3 cos delta times cos theta t minus a3 sine delta sine theta t, and that's equal to, using this expression up here, all right, that gives us then that a3 is cos theta t plus delta. So from the trigonometric identity for the cosine of the sum of the two angles, so we get that from this expression, we get, this is the trigonometric relationship, and when we plug that in, we get that the general solution is yt times rt a3 cos theta t plus delta. Values of r and theta come from the structure of the original difference equation. So r squared is equal to alpha squared plus beta squared, as we noted before, which is equal to minus a1 over 2a0 squared, plus this expression here. This is the solution, of course, to a quadratic, and we square that, which then, if you look at it, you'll see that it solves to a2 divided by a0. The cos of theta is equal to minus a1 over 2 times square root of a0 a2, or the tangent of theta is beta over alpha, and that's equal to minus 1 over a1 times square root of this expression here. So this is just the quadratic formula for finding the x1 and x2 in the auxiliary equation. So alpha, a3 and delta are derived from a1 and a2, as we noted above, which in turn come from the initial conditions c0 and c1. Now consider again the equation, or the solution to yt, is equal to r to the power t multiplied by a3 cos theta t plus delta. This is a periodic function characterized by three parameters: a3, theta, and delta. So we can identify the amplitude as the height of the peak above or the depth of the trough below some average level. As phi ranges from 0 to 2 pi radians, cos phi ranges from 1 through 0 to minus 1 and then repeats. A3 multiplies values of the cosine, thereby determining the amplitude. So it'll raise it from this minus 1, from this 1 and minus 1 to higher or lower values. The period is the range of the independent variable during one complete oscillation. So cos of t has a range of 2 pi, but for cos theta t, the period is given by 2 pi over theta. If theta is greater than 1, repetitions occur more often, but less often if theta is less than 1. So think of it as squeezing the, if we go back to this diagram, as squeezing the cos function so that the oscillations come like this. They're much tighter than they were before, or they're much more less tight, if you like. So that's the period. The phase is the value of the independent variable at the first peak or trough. For cos phi, it is at phi equals 0. Clearly, for cos t and cos theta t, it occurs at t equals 0. For cos t plus delta, it occurs at t equals minus delta, and for cos theta t plus delta, it occurs at minus delta over theta. So delta shifts the function rightward or leftward on the horizontal axis. Finally, RT magnifies because R is greater than 1, or dampens because R is less than 1, the amplitude. Now what you can do is, if you like, simply go into Excel and play around with values of delta and theta and all of these values to see what exactly happens to the amplitude, to the phase, and the period as these things change. So let's look at an example. Yt plus 2 minus 12 yt plus 1. That should be a plus here. And then plus 100 yt equals 0, y0 equals 5, y1 equals 12. These are our initial conditions. So we get this operator form equation, e squared minus 12e plus 100 multiplied by yt equals 0. X squared minus 12x plus 100 equals 0 is our characteristic or auxiliary equation. Then using the quadratic formula, we find that we get 6 plus or minus 8i. And now consider this general solution here. And that gives us k1 multiplied by 6 plus 8i to the power t plus k2 6 minus 8i to the power t. Given the initial conditions that y is 0 is 5 and y1 is 12, we get k1 plus k2 equals 5. So if we have 0 here, then this becomes a 1, this becomes a 1, and we have, if t equals 1, then we have 6 plus 8i all multiplied by k1 plus 6 minus 8i all multiplied by k2 is equal to 12. The solutions are that k1 is 20i minus 9 over 8i and k2 is 20i plus 9 over 8i. The complete solution then is that yt is equal to 20i minus 9 over 8i multiplied by 6 plus 8i to the power t, and that add to that 20i minus 9 over 8i times 6 minus 8i to the power t. Now consider the alternative method of expressing that solution. Yt equals RT to the a1 cos theta t plus a2 theta sine theta t. That gives that RT is a3 cos theta t plus delta. A1 equals 5. A2 is minus 9 over 4. R squared equals 100 because cos theta is 6 over 10 and theta is 0.927 rads. So now what we get is that yt is equal to 10 to the t multiplied by 5 cos 0.927 t minus 9/4 sine 9275 t. And where do some of those come from? Well, they come from these initial conditions. So then yt is 10 to the power t, 5 cos 0.927 t minus 9/4 sine 0.927, and then also multiplied by t. So further, the tangent of delta is equal to minus, remember this is that value of a1 divided by, of a2, which we get here, minus 9/4. So we have the formula minus a2 over a1, so we have minus 9/4 over 5, and those come from here, and that's equal to 0.45. Recall that the tangent delta is minus a2 over a1. Delta turns out to be 0.4698 rads, and we get that from the arctan, so tan minus 1 on your calculator, of 0.45, which is 26.91972. So delta is 26.91972 degrees. We multiply that by pi over 180 to convert it to rads. This is a degree sign here. And the sine of delta is then 41036, and the cos of delta is 91192. And I'm just checking those numbers there. A3 then is given by A1 over cos delta, and that gives us 5 over 0.91192, which gives us 5.48294. So then the final solution in this form is given by yt equals 10 to the power t, 5.48 times cos of the expression 0.927t plus 0.4698. Now, just for a quick review, here we have the hypotenuse, the adjacent, opposite, theta. Tan theta is opposite over adjacent. Sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. We convert degrees to radians using 1 degree times pi over 180. That gives us 0.01745 radians per degree. And the angle in degrees is the arctan, or tan minus 1, of the tangent theta. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.